And as Emilio said, I'm kind of the introductory speaker for some coming attractions, the first one of which will be next week. And my last slide will show you exactly who you're going to hear and what the topics are. But I wanted to introduce generally, very non-technically, although I can get really technical if you like. And I hope it's mostly Q&A. So I have a few slides here. If I don't get carried away and engaged with them, I hope to get through them fairly quickly so you guys can ask questions. And I should tell you at the beginning, I'm the guy that loves to be interrupted. So don't hesitate to yell out a question, or if I don't happen to see your hand, just whisper in Emilio's ear. He doesn't mind interrupting me, and I don't mind it either. So here we are. So anyway, here's what I want to talk a little bit about personal electronics very briefly, because that's not us. Then about transportation and the electricity grid. What's JCESR up to? It's really quite different, quite innovative. We hope it works. It's a new way of doing business. It's also a new way of doing research. So, and then a little bit about the technologies we're following, and then what are the coming attractions. So that's it. If you want to read more, two things I can recommend. Our webpage, which is right here, changes all the time. We have some really good web folks, thanks to Ben, who's sitting right there. And it's like browsing the New York Times. So you can read a lot there without getting bored. Here's a paper, a review article that's a little bit out of date. It's probably 6 months out of date by now, or a little bit more. But it's on archive. It's also published, and you can download it there if you want to know more. A lot of it is this talk. So here's what we know about lithium-ion batteries today. Lithium-ion battery was introduced in 1991. It enabled all the personal electronics that you see here and even more. I don't see the Apple Watch there, for example. But it was a revolution. And it changed the way we basically interact with information and interact with people. So it has changed really everything. If you ask what's the limitation of personal electronics today, still the battery. So here's an X-ray view of your Mac, and you see most of it is battery. The logic doesn't take up any space at all. There's a trackpad, and the rest is battery. So everybody wants a longer lasting battery for your cell phone for sure, because then you could load it up with even more apps and make even fewer actual phone calls, but you would use it for a lot more convenience in your life. So that's what we have today. But the little batteries that work on these things don't really work for cars, and they don't really work for the grid, because they're just not powerful enough. You can't get enough juice in them, and they cost too much. So the two things that are waiting to happen are electric cars at the 20K level, not the 80K level that we'd all love to have a Tesla. And we're far from that. The major problem is the battery. Here's all the good things about electric cars, and there's lots of them. Good reasons to do it. The second thing is grid-scale electricity storage, and that means basically breaking the age-old, that is going back to Thomas Edison's time, so that's forever in terms of the grid, that constraint that you have to produce electricity over here at precisely and instantaneously the same rate that you use it. So we know how to do that because demand is pretty predictable. You're not going to need much at 2 in the morning. You really will need it at 6 in the afternoon. And day to day, you can probably guess what that would be within 3%. Wind and solar change that. Here are variable sources that if they come out at the 20% of our electricity level, which everyone predicts, and some people, in particular New York State and California, say 50%, then if the sun doesn't shine one day or if the wind doesn't blow, you're really in trouble. You can't afford to lose 20% or 50% of your electricity. So what do? You back it up with a gas plant. You build a gas plant right next to the wind farm, and on the few days that the wind doesn't blow, you turn on the gas plant. That's what you do now because a battery is too expensive. So the whole goal is to get the cost down for a really big battery that you would want on the grid so that you can start to charge in the middle of the night when there's excess electricity and discharge at 6 o'clock in the afternoon when you really, really need it. So just to give you a perspective, Here's all the energy the U.S. used in 2013. The two biggest sectors are in color. The grid, about 40%. Transportation, that's the gas in your tank, about 28%. Together, they account for 2/3 of all the energy that the U.S. used. And let's ask a little pop quiz here. For personal electronics, everything powered by a lithium-ion battery, your cell phone and so on, what percentage of the U.S. energy use do you think that is? Anybody want to take a guess at that? 5%? Any other guess? 1%? You guys are way too smart. It's something like 2%. So you could imagine if you could channel half of the energy that goes into transportation and the grid through batteries, use storage in that way, it's a 10 times bigger market. So it's a huge opportunity. So that's what JCESR wants to do. Its vision is there: transform transportation and the electricity grid with high-performance, low-cost energy storage. Here's the mission. So we have a 5-year contract, and I should say that timescale is not our choice. We were told you can apply for a 5-year contract along with everyone else, and we did. So here's what we said we were going to do: deliver storage with 5 times the energy density, that's what you need for the car, and 1/5 the cost, that's what you need for the grid, of commercial batteries. It says today's, that's really 2012, that's when we submitted our proposal, and do it within 5 years. Really aggressive, but transformative vision. We could have had a smaller vision, but we didn't want to have a smaller vision. We wanted to have big impact. So that's our mission. We want to leave behind 3 things. We call them legacies, 3 legacies. First one, a library of fundamental science about the materials and phenomena of energy storage at the atomic and molecular level. We've had about 15 years of nanoscience, and frankly, that nanoscience has not been applied at the level it could be to the energy storage problem. So there's a lot of headroom that one can access there. It's also not the way the battery R&D community typically works. It usually says lithium-ion battery, the weak link is the cathode. I'm going to make a better cathode. Let me try this. If it works, I'll use it. Doesn't work, I'll throw it away and I'll try something else. But I won't ask the question of why did it work or why did it fail. And we think you ought to ask that question and you ought to answer that question, because once you understand what it is you need and why things either work or don't work, you can pick the next material a lot faster. And once you pick it, you can get the most out of it by understanding what it's supposed to do. So this library of fundamental science will publish. Everybody in the community will be able to use it. It'll kind of lift all ships. And we think that's a fundamental difference for the way business is done now. The second legacy is 2 prototypes, one for the grid, one for the car. Probably look really different because you want a little tiny, high-powered, ultra-cheap thing for the car. Grid, it can be a little bigger. You can control the environment, put it in a shed. It doesn't have to work when it's 0 degrees out or 90 degrees out. So they'll look different, but they may be based on the same library of fundamental science. And the third legacy, which may be the most important, is a new paradigm, as we call it, for battery R&D that combines 4 things in one highly interactive organization. So the 4 things are discovery science, battery design, research prototyping, and manufacturing collaboration. This is, again, not the way the battery community works. Usually discoveries are made maybe by university groups who publish their paper, they're done. Somebody else has to see that paper and decide it's interesting and take up that research direction. A third group has to actually put it into a battery, make the system, and a fourth group, the manufacturer, actually sells it. So we won't manufacture, but we'll talk to manufacturers and do all of this in one really highly interactive organization. So here are the 4 things. This is our so-called functional diagram. So we do science over here. I'll tell you what these 3 things are. We do battery design, we do prototyping, and we talk to manufacturers about what would be interesting to them and what we should do and shouldn't do. We bring some special tools to the table. So we have the materials project and the electrolyte genome. These are both genomic style things. Before JCESR, there was a materials project that looked at electrodes, crystalline electrodes, anode and cathode. on the computer, simulated their properties and asked which one of these is best. We've taken it to a new level now, and we have now published papers as of about, I think, 6 or 8 months ago on cathodes for multivalent batteries, which I'll tell you about. 2,000 combinations of cathode and working ion, and the idea is we may find 1 or 2 out of those 2,000 that are really look promising and are worth making in the laboratory. You could never make all 2,000 in the laboratory, impossible. So this really speeds things up. A new thing that JCESR did was say, let's apply the same genomic idea to the electrolyte. So the electrolyte is typically a liquid organic electrolyte. Totally different way of calculating, because atoms move around and molecules in the liquid. But nevertheless, apply the same techniques. We now completed a couple months ago 16,000 organic molecules in the electrolyte genome database, which could make up electrolytes or maybe salt anions and solvents and all kinds of things. So we're now sifting through that database to find the things that really work. Second thing is an electrochemical discovery lab. This sits in the ESB. It's to look at the interface. So the crystalline electrode, the liquid electrolyte, that's where all the electrochemistry takes place in a battery or any other electrochemical system. And you want to know how is charge transferred, how are ions transferred, they are stripped off, they're deposited, they go into intercalated sites, all kinds of things. So we both make these things, very pure electrolytes, and measure with the latest equipment. You see some X-rays and IR and even light coming in and out, and STMs and NMR and all kinds of things go into that. So it's state of the art. The third thing is techno-economic modeling. That means very much like this, except model the whole battery on the computer. So anode, cathode, electrolyte, all working together, and find out, predict 2 things. How would it perform? That's the first 5 we want to go after. And what would it cost to manufacture? That's the second 5. So that really helps you filter going this way. You'll only make the prototypes that look promising instead of all of them. But it also helps you going this way. We say we want 5 times better performance, 1/5 the cost. We use this program going backwards to project out what materials, performance, and cost thresholds do we have here for the anode, the cathode, and the electrolyte in order to achieve those aggressive 5 times goals. So really helpful system. The fourth thing is a thing we call sprints. So we organize a lot of our research by, it's structured or punctuated. So we say, we want to make this prototype, we think we can make it, but we can't make it unless this, and this work. So we take the first one, the biggest challenge, and we say, let's see if this works. And we'll make a team of maybe 5 to 15 people, taken from 160, which are in JCESR, if you count all the postdocs and graduate students. And we'll say, answer this question. Will this idea work? Will this material work? They have maybe 4 to 6 months to answer it, because it's just one question. At the end of that time, they've answered it. They publish a paper if there's something publishable there. They propagate the results within JCESR, and we might say, okay, it worked, let's go to the next question, or it didn't work and it will never work, so we'll drop it. And that helps us to not get stuck in dead ends and to keep the process moving. Everyone knows why they're here, what they're doing, and what they're trying to accomplish. So that we now have 12 sprints completed, I think 5 more underway. Interesting thing we found out about the sprints, when they're led by early career research people, so even postdocs, they do a lot better than when they're led by senior people. And I think the reason is that senior people, they have a lot on their plate and they can't give it full attention. The early career people really can. So it's a great leadership experience for these people. And of course, the first time you try to lead, you make a few mistakes. Okay, so make a few mistakes. This thing's over in 4 to 6 months. It's behind you and you can do better next time. Really a nice thing. So let me now tell you how a lithium-ion battery works, if I can. Whoops, looks like this is not going to work. So I'll just skip it. And I'll tell you this is an animation of this thing. So there's a cathode, an anode, typically for lithium-ion it's graphite. The lithium ions sit between the layers of the graphite. They're intercalated. When you want to discharge the battery, you close the external circuit, which lets electrons flow from anode to cathode. And the lithium ion flows inside this liquid electrolyte, single positive charge to balance the single negative charge of the electron, over to the cathode, and the lithium intercalates into the cathode. And it's reunited with the electron, which goes in the external circuit. So you see the electron in the external circuit. You don't see all this stuff which is inside the battery, but it's pretty complicated. So it's sometimes called a rocking chair. It stores energy in one state. The lithium is in the anode. The energy is stored. The lithium goes to the cathode. It rocks to the other state. It releases the energy. It stores energy. It releases, and so on. So that's what it does. So what do we want to do? Well, we have three ideas. I showed you these three lines on our functional diagram. First one is, well, lithium has one charge. Let's replace that with magnesium, which has two charges. Or calcium has two charges, or zinc has two charges, or aluminum has three charges. So on the back of an envelope, or let's say in principle, you've doubled or tripled the energy stored and released with every ion that goes back and forth. Really easy way to up the energy density. The trouble is that all of the anodes, electrolytes, and cathodes that work for lithium don't work for magnesium. So you have to rediscover all three of these first materials, make them into components, and make those components into a battery. So that's the first idea. Second idea is, let's get rid of intercalation. So this host, this graphite, or this metal oxide for the cathode, are sitting there all the time, whether they have lithium in them or not. So they're taking up space and they weigh something, even when there's no lithium, when they're not hosting any lithium. So let's replace that intercalation with a chemical reaction. And the thing we're looking at most closely is a sulfur cathode. And you have a chemical reaction between lithium and sulfur, which stores a lot of energy in those covalent bonds, chemical bonds, more energy than you could store here, maybe 10 times more. So that's the second idea. The problem is, of course, that sulfur is an insulator. Lithium-2S, which is what you make from that chemical reaction, is also an insulator. And it's very hard to reverse that reaction with access to electrons. You need some other way to do it. The favored way is make a very thin nanostructured film or some other structure, because the surface of the lithium-2S you can access with electrons. If it's all surface, then in principle you can access the whole thing. That's the second idea. Here's the third one. Get rid of the crystalline electrodes altogether. Replace them with a liquid. So it could be a solution, so ions in solution. It could be a suspension, nanoparticles suspended in a liquid. And the reason you want to do that is for grid applications. This scales trivially. Make the liquid tank bigger, you're storing more energy. And it scales, as big as you want. There's no limit to that. There are other reasons. If one of our ideas is that you could use organics as the active materials here in a flow battery. The typical flow batteries that are out there use transition metals. They have two oxidation states. With some organic molecules, you can get as many as 6 different oxidations. That is, oxidation states that differ by 6 charges. So probably those are not going to work for a battery, but 2 or 4 or even 5 oxidation states might. So the organic materials, they're abundant, they're cheap. If you break them down completely, they can be recycled. So there's a lot of advantages. Plus, there's lots of variations. There's far more organic materials you can make from just 6 or 7 atoms than inorganic. So there's the idea. Now, this actually is a really important slide comparing lithium-ion to beyond lithium-ion, as we call it. So plotted here, systems, and by that I mean what kind of concepts do you use to construct the battery? For lithium-ion, it's intercalation at the anode and cathode. Here, materials, how many materials can you use to make this battery? So here's lithium-ion, been around since '91, almost 25 years. We know a lot about it. And you can still make incremental improvements remarkably the energy density of lithium-ion batteries goes up by about 5% a year, and it's done that for 2 decades. It's really, nothing has ever come close to that. It's a phenomenal record of achievement. But they are incremental. It's 5%. It's not factors of 5. Very simple systems here, as I was saying, intercalation on both sides. There may be 6 or 7 materials that are used to make those lithium-ion batteries. By contrast, here's the beyond lithium-ion space. It's way bigger. So I mentioned 3 ways of 3 ideas we're following: multivalent, chemical reactions, and flow. You can apply those at the anode or the cathode. 3 times 3 is 9, I believe. And the electrolyte could be solid or liquid, so 18 times 2, 18. 18 different ways to conceptualize a beyond lithium-ion battery, at least, compared to 1 thing for lithium-ion. So there's a lot of richness there. And the materials, there are probably 30 or 40 materials that are under consideration to implement all these different ways of these different concepts. So there's something like, conservatively speaking, 50 to 100 batteries in that beyond lithium-ion space. If you're Thomas Edison and you say, well, 2% inspiration and 98% perspiration, I'll try the first one. If that doesn't work, I'll try the second one. If that doesn't work, you won't get anywhere. You need a different approach completely to look at this landscape of that beyond lithium-ion space and immediately trash the 80% that are probably not going to work and focus on the 20% that at least have a chance of working. And that's what we do with our genomic approach to materials, with our techno-economic modeling of battery systems, and with the electrochemical discovery lab that has comparative data on all the different interfacial effects taken by the same methodology. So we can do that comparison, and that's critical. Here's the kind of battery we want to make. So in our first review, which was 8 months after we launched, one of the reviewers said, oh, well, you'll make a prototype, you'll stick it under the hood of a Chevy Volt, drive it around for a couple of months and see how it works. No, that's way too much for us. So we're going to make a prototype that I can hold in my hand. It might have wires hanging off. It might look pretty messy, like a lab thing, so like this. Or it might be a little more finished, like that. And when we're successful, when we get to this point, we'll hand it off to a manufacturer like Johnson Controls, which is one of our 14 partners, just across the state line in Milwaukee. And they'll make a product prototype that maybe you would put under the hood of a Chevy Volt. That is actually the battery of the Chevy Volt, and drive it around and see how it works. So we're 1 step below that. And to answer, because we got that question, we realized that we have to clarify what we're going to make. We made this chart. So you may have heard of technology readiness levels, which is used by the military all the time and also industry to know how close are you to actually having something that you might turn into a product. We stole that idea and put the word battery in front of it. So battery technology readiness levels. And they're levels. So level 1 or 0 might, I guess we call it 1 here, might be a scientific phenomena that you discover that you might be able to use in a battery, but no, that's it. Next level up, maybe there's a set of materials, a class of materials that exhibits this phenomena that you could use. Next level up, you might make a half cell. So it means an anode and an electrolyte and some phony cathode that's just there to give you some ions. And you look really at the interface between the anode and the electrolyte. How do they work together? You can do that also with the cathode and the electrolyte with some phony anode. And if that works pretty well, then you might say, let's make a full cell. Let's take an anode, a cathode, an electrolyte, put them all together and see how it works. That's our sweet spot. That's kind of where JCESR targets something that we might then take lots of data on, plug that data into the techno-economic model, and project that if you manufactured it, this would give you, let's say, the factors of 5 that we're looking for. So that's the idea. So where are we now? So at first year and a half, we were looking around in this big blue space for ideas. Last October, almost a year ago, we selected 4 that we think look promising. These are the 4. 2 for the grid, 2 for transportation. Let's go down here for the car first. I mentioned multivalent. We actually think magnesium is the best working ion. We have 2 cathodes, V2O5 and manganese oxide spinel, that we know will accept magnesium as intercalants. And we've actually developed in the last year 2 new electrolytes that almost might work. I think they're actually not quite good enough, but they're way better than what was there before, so you might project that we will get to the right electrolyte. And we want to make this into a prototype. So the other one, these 2, there's one grid and one car battery, lithium sulfur. They suffer from the same problem. When you have a lithium sulfur reaction, it doesn't go directly to lithium 2s. It goes through 4 or 5 intermediate states. So it's lithium 2s2 minus minus, lithium 2s4 minus minus, s6 minus minus. And these intermediate polysulfides, as they're called, are soluble in the electrolyte. They migrate from the cathode over to the anode, short out the battery, and basically you're done at that stage. So the trick is to find a way to contain those polysulfides, on the cathode side. And we have 3 ideas for that. That will enable both of these batteries. And the redox flow battery, really exciting last year, instead of having molecules in solution for the flow battery, we started out saying, well, why don't you take those active molecules and string them on a polymer? So there's little side ligands, side chains on the polymer. And that polymer then you can filter, because it's a big thing, like a protein, with just a simple size-selective porous filter, you might be able to filter it. And then this year we said, well, there's a better idea. Why don't we cross-link that polymer so it forms a colloid, which is a micron in size, perhaps that big, 3/4 of a micron. It's roughly spherical, and that thing is even easier to filter. So you buy for $1 off the shelf a CellGuard filter that's size-selective porous, and it filters 100%. So it's really a brilliant, I think, innovation. Nobody else thought of this. We have showed in the last few months that it looks like it actually would work. And that's the way we're going. So ROM means redox organic molecule, less than a nanometer. Redox active polymer, that was the first idea, and redox active colloid. So those are the ideas that we're following. We want to get there, proof of concept prototype, and we do that by converging. And we have invented, actually stolen, 2 names. The first one is convergent research. Here's some ideas that look like they might work, but we don't actually have a full system. That's what we have to converge. So here we have maybe 4 questions that have to be answered yes. If we're going to get from here to here, we form 4 sprints in principle, for example, and we start answering the question yes, 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 no. Failure, but we've got other ideas here. This is more than one battery. And you go back your second idea and see if it works. So this is the idea of convergent research. It's really important to have the second kind of research, divergent research. So when we started with that big blue space, it was all divergent. And by that we mean maybe it's this, maybe it's that, maybe it's that, maybe it's that. We'll find the best idea. And once we identify the idea from divergent research, we'll converge it. Well, you find out in lithium-ion history, and of course beyond lithium-ion as well, most of your ideas to converge don't work. There's lots of reasons why, side reactions that you didn't know about, lots of things that basically induce failure. So you need backup ideas. So we're going to keep doing divergent research all the way to the end of the 5 years as backup for the things that we expect to fail. So here's 4 ideas. There are actually more than 4 batteries there. Half of them will certainly fail, and maybe 3/4 of them will. So we want to have some divergent research to back it up with some different ideas. So I'm done. Here's what you're going to hear next week. Justin Connell will be here to talk about the Electrochemical Discovery Lab. I think, I have to push that. So he'll tell about that. It's really very exciting. Kevin Gallagher on September 17th will talk about transportation batteries. The two that we're looking at now are magnesium with 2 ions and lithium sulfur. So cartoons of what he'll be talking about. On the 24th of September, Jeff Moore and Joaquin Rodriguez-Lopez from UIUC, partners in JCESR, will talk about flow batteries and this idea of first a polymer, then cross-linking the polymer to make a colloid, and then a simple size selective filter that keeps the active materials apart in the flow battery. And then, on October 1st, Jeff Chamberlain will talk about a new argon program, initiative, called Access. It does stand for something, but it's much more important that you be able to pronounce it. So it's called Access. And it combines the beyond lithium-ion things that JCESR is doing and the decades-old lithium-ion research that's already predates JCESR at Argonne, and for which Argonne was really well known. And I'm sure one of the reasons that we were awarded the JCESR contract was that foundation. But it unites them. As if you go out in the community, everybody's doing lithium-ion. There's no applications for beyond lithium-ion. We're going to have to get our beyond lithium-ion prototypes accepted by a community that knows nothing about them. So where do they fit into the spectrum? How would you use them? Want to have these relationships with manufacturers and end users. Jeff already has a lot of those relationships, and he's developing more. So this is really looking forward very strategically to the next step. And he'll tell you all about that. So I'm done. Anybody have any questions? I would love to answer them. Thank you. There's one.
George, a lot of complex models have input that is uncertain. So you don't know exactly a rate, you don't know exactly a cost.
Yeah.
And part of your step is to take the basics of the search, put it into a model, and have it go both towards
Yeah.
development and back to the basic research.
Right.
So that, I'm wondering if that gets you into the uncertainty quantification of the theory. Do you do any of that?
Great question, and it obviously right at the center of what we're doing. So look, a couple stories, and I will answer the question. The techno-economic model that we have was developed pretty much at Argonne by Paul Nelson and Kevin Gallagher a while ago, 5 to 10 years ago, for lithium-ion, and is now used by almost everybody in the field. Some variation of it is used. GM uses it, for example. It's open source. GM takes the open source and twiddles it, of course, and they don't tell you what they've done. But it's based on Argonne's techno-economic model. So that is pretty well established and credible for lithium-ion. Now, if you say, let's apply it to beyond lithium-ion, then the challenges that Al is talking about come into play. Well, you don't really know. You can't validate that, so you're kind of dead reckoning, going by the seat of your pants. Yes, but we understand, and especially Kevin Gallagher understands, how these things fit together in lithium-ion, and has so much experience with it that you can see some of the problems and anticipate them and maybe fix them before they happen. There will be a certain amount of uncertainty that you can't get away from. There's no doubt about that. I think if we were able to predict to the 10% level, we'd be thrilled. We might be able to do it to the 20% level, and frankly, we don't know how good we are. I don't think I have any slides here of his predictions, but they're not points on a graph. They're bubbles on a graph. So he doesn't claim to have a precise prediction. He has a range of things. It might be somewhere within this bubble. And I think, honestly speaking, that's about the best you can do. So we're aware of that. I'm not sure there's any answer to that question until you finally start to make some systems. Yeah.
Engine model, combustion, there's the same sort of issue. And part of the deal is to decompose that bubble into sources.
Yeah.
And there has been in recent years a lot of technology developed that helps do that. So that you not only have some band of uncertainty, but you know who are the main actors in contributing to that kind of uncertainty. And since you basically have feedback loops in several different directions, to the degree that you might be able to decompose uncertainty, that could
So, great point. And in fact, that's exactly what Kevin and company do. So they look, for example, at the cost of the battery. Well, how much of each material do you need? What is the cost of that material? You know what it is now. If you made 3 million batteries out of it, maybe the cost would go up a little bit. So there's an uncertainty there. Or it just simply fluctuates in time. There's an uncertainty there. Maybe you need a little bit more than you thought you needed. There's an uncertainty there. But you can quantify if you say, just to take a number out of the air, we'll assume a 5% uncertainty in all of those things. Then the total cost of the battery, you can calculate the uncertainty for that. So they do that. And I didn't realize this would be so interesting. I should have brought one of the graphs, which actually breaks the cost down into, I think it's 5 or 6 different components, and shows a bar for each one of them. And they're arranged visually beautifully so that if you slide them along, you get the total cost and the total uncertainty. But exactly that kind of thing is done. You do it for the performance side as well. So, great point.
I wonder if you might comment on how you feed that cost into research. Just as an example,
Yeah.
in answer, we studied iridium showers for water oxidation, not because iridium, unless another meteorite hits it,
For the dinosaurs. Yeah.
very abundant, but because understanding how it works
Yeah.
gives you insights into how to make the base methods work. So how do you balance that issue where you say, I don't look at that, this is just good.
So, in fact, a couple of comments on that. Great question. Maybe I'll flip back here. This techno-economic modeling, I mentioned, and Al emphasized, we like to go both ways with it. That means we know we want a factor of 5 lower cost and factor of 5 higher performance. What does that mean for the materials over here? So there are now thresholds, and there is an eye chart somewhere in my backup slides, for every prototype that we're thinking about, every concept that we're thinking about, what's the threshold level of performance for that material? And those actually cut out some things. There's another set for the threshold cost of the raw materials. And because of that, we just throw some things away. I think we're at an early enough stage that apart from the things we throw away, we don't know yet how close we'll come to our target, but we know that, again, we have this bubble, that it's possible to achieve within that bubble a certain cost or a certain performance. And until we know better, we're going to assume that we can get it. But, great question.
George,
Yeah.
let me ask you one thing.
Yes.
So you are getting close to the 3 years for JCESR.
Yeah.
And in about a year from now, you're going to have to start thinking about what you're going to do for the future.
Right.
So have you given any thought about what direction to go with JCESR for the renewal if that happens to be the case?
Absolutely. Is this being recorded?
Can you turn it off?
So we have to give thought to that. It would be, irresponsible not to do that. So there are many things that you could think about. So we're 2.5 years in. We have these 4 ideas. Some of them may work. I mean, we actually see the light at the end of the tunnel, and we may get to the end of the tunnel in 5 years. That would be great. Then you might say, or a critic might say, you made the prototypes, you're done. You don't need the second 5 years. We would say, yes, we have the prototype. It's not manufactured yet, and it hasn't been improved yet. So if you look at lithium-ion, after 1991, it was about a factor of 2 better in performance than the next best battery, which was nickel metal hydride or nickel cadmium, either one. It's about a factor of 2 better. It's gotten a factor of 3 better in the time since 1991. So now it's about a factor of 6 better than what was around in 1991. You won't get that additional improvement after commercialization without a lot of research. Who knows more about that prototype than we? No one. So why don't we start working on improving the post-commercialization, well, either assisting in the manufacturing, and if it does get manufactured within the 5 years.
If you go back to your slide with timeline,
Yeah.
so you will be targeting the last column? That one?
Yeah. So if we got here in 5 years, There's another thing that's equally,
The 5 to 10 years, that's a slide that we have 1 or 2 years, 3 years, and so on. So
Yeah.
would you think about moving into that space?
absolutely. And actually, so I think there's another click here. Yeah. This divergent research is critical. So that's one option. Another one is, oh, you got a prototype, but that big blue space is so big, there's another one there. There's two solutions.
Recycle.
Well, we can develop another one, which might turn out to be better than the first one, or at least as good, or maybe useful for a different grid application. There's 17, as Sandia tells us, 17 applications for storage on the grid. They're not all going to need the same battery. So maybe we'll develop a different kind of beyond lithium-ion battery for some of those applications. And that's why we keep doing divergent research. So if we're lucky enough to succeed here, then we'll go back to our divergent research reserve, and we'll say, well, here's the next idea we're going to develop, and we're going to need that. So that's another outcome. A third outcome is, well, we didn't actually get the factors of 5 that we want, but our we've made a lot of progress in electrolytes or cathodes, and we see a pathway to getting the full factor of 5. We need another 2 or 3 years to do that. Let's make that the basis of the renewal. There's all kinds of things, and I think we all agree that in the renewal period, we have to do something different than what we're doing in this first 5 years. So this thing, starting with 0 basically, in the first 5 years, we can't repeat that. We have to get closer to manufacturing, we have to get closer to applications, we have to develop more than one battery. Not clear exactly what path will be the best, but I think we have enough ideas that we can write that proposal when the time comes. That's what we think.
Yeah, so on your slide when you're talking about the battery technology readiness levels,
Yeah.
it seems like you're making a proof of concept and then you're kind of passing off that technology to the manufacturers. I'm wondering if you thought about what you need to do in the intermediate for like small scale testing and maybe looking at the niche markets. Are you planning on working on any of that kind of stuff as well?
So a great question. So our stated goal and what we've agreed to do with our sponsor is to make these prototypes, and we actually haven't specified or been asked to specify where they would go. We just say we're going to give them to manufacturing. There are plenty of niche markets, and I was mentioning this Sandia report was from 2010, said there's 17 ways to use storage on the grid. It listed them, it described them, it didn't really analyze them. So one of them might be, I've got, as happens now in California, I have rooftop solar, and in the afternoon I got plenty of solar electricity. I actually don't have to run my conventional plants much. But at 6 o'clock, sun goes down, I got a problem because I suddenly lost that. Wouldn't you like to store some of that excess in a battery and time shift it maybe 4 hours until 6 o'clock and start to release? So as it happens, it's already profitable with lithium-ion batteries in certain places in Southern California to do that. And a company called AES has lithium-ion batteries on trucks that they park in Southern California and make money doing this. So it's probably the only place in the country you can do that. It's an unusual application. Well, that's one application. Another one is frequency modulation. You want to, on a 1 second time scale, release a lot of energy into the grid or absorb a lot of energy from the grid because the load, whoever we consumers are, varies on that time scale by 20 megawatts or something. So there's another company in Chicago called Intelligent Generation that goes after that market. And it turns out in PJM, which Chicago is part of, it's profitable to do that. You can make money at that too. These are niches, and we would love to take a battery, of course not a prototype like this, but maybe our manufacturing partner would make a prototype, that product prototype, that would get tested out not under the hood of a Volt, but in the grid with one of these two or another application. So we're now starting to talk with two outside agencies. One is EPRI, Electric Power Research Institute, which is in California. They represent utilities. And the other is Navigant, which is a sort of a market analysis firm. to develop the use cases for these 17 uses for batteries on the grid. And our goal is, of course, ulterior. We want to make such an exciting case for some of those 17 that somebody else in the community, maybe a startup, says, oh, there's an opportunity there for me. I want to work with JCESR to make this happen. So we're trying to, in a sense, create market or create market enthusiasm from these kinds of roadmap studies. So we're certainly thinking along those lines.
Supposing you got a question from someone like Bill Foster, which I did, asking how you're doing. Have you gotten teaching through? Have you developed any fascinating new material? How would you answer?
Yep, it's really easy to answer that question. Let me start with a general answer, which is right here. So I didn't mention this, but in going from here to here, there's really three things you have to do. You have to discover the materials, and we used a techno-economic model to tell us what the thresholds are, which materials will qualify. You have to find those materials. You have to make them into components. So if you want to make an anode or a cathode, it's not the raw material. It has to have certain properties and maybe a coating on the surface and so on. And then you have to make those three components, anode, cathode, electrolyte, you have to integrate them into a cell. So there's no reason that this should be linear. We're halfway through 5 years. We shouldn't be at 2.5, 2.5, 2.5. Just doesn't work that way. Instead, every project that I've ever been involved in, and certainly the lithium-ion battery itself shows this dramatically. Here's time. Here's 5, 5, 5. You're going to go like this, and then in the last year, you'll suddenly put all this stuff together that you've been working on, and you'll get it or you won't get it. But you can't tell from where you are in 2.5 years whether you're going to make the 5-year mark or not. So that's a very general answer. There are specific answers, and I didn't put the details here. But for every one of these ideas, we have significant progress in the last year, not even counting 2.5 years, but the last year. We've discovered 2 new electrolytes for the magnesium battery. We've discovered a new cathode for the magnesium battery. One pre-existed us, the other we discovered. We discovered this idea of why don't you take the active materials and make polymers, and then take those polymers and make colloids. That's virgin territory. Nothing is known about that, and it's so wide open. I mean, we clearly have to rebalance our research program now to take into account these opportunities. We're not there before because we discovered them. Now we have to decide how much resource to put on each one of those. What are they worth? So I think there's plenty. I sometimes use the phrase light at the end of the tunnel. We see the light. The light is really there. So we know where we're going. And will you get there or not? Well, I hate to predict the future, because usually that's wrong. But I think there's reason for hope. I would say we're in a very good place. So we certainly have the chance to succeed in 5 years. Oh, you got some more questions.
And we're going to fill it up after 1 hour.
Good.
So another choice in looking for funding and how to extend this, sort of, you brought up Tesla with the billion-dollar battery plant.
Yep.
Right? So money in startups and in collaboration with industry is one way. Sort of aircraft carrier level. Right? So here's another place maybe to think about going forward, particularly with investment.
For sure, and since you mentioned Tesla, so I have enormous respect and admiration for Elon Musk. He's innovated many times, and he's won many times. Not every time, but he's won many times. And the Tesla certainly looks like a winner. So now he's saying to himself, I'm using computer batteries in the Tesla. Why don't I make the batteries? I'll design and make the battery for the Tesla instead of for a computer. And I'll, number one, save money because, economies of scale. I'll be my own supplier. And people say he can make the battery for 30% less, and I think that's credible. Everyone believes that. So that's quite a jump for his business. But when he said gigafactory, I think he realized, that's a lot of batteries. So what am I going to do with that? Well, let's put some of those batteries in garages. Let's make the power wall. And we'll pair a battery in the garage with a solar panel on the roof, And I won't sell any of my solar electricity that I get in the afternoon. I won't sell it back to the utility. I'll put it in my own battery. I'll keep it, and I'll use it at night. So a brand new paradigm for what do you do with solar panels. I think it's more or less brilliant. I think of it as cell phones, all over again, deja vu. Cell phone doesn't look anything like the landlines we used to have. You put a battery in the basement, or the garage is a better place, and a solar panel on the roof, and that's not going to look like any utility system that we ever had before. I was at a talk, and I see somebody in the audience that was at that talk a couple days ago, where Sonny Garg used to work for Exelon and ComEd. He said, you bring back Alexander Graham Bell now, and you show him this thing. And he'll say, what is that? I don't know what you're talking about. What is that? You bring back Thomas Edison and show him the grid, and he'll say, oh yeah, I understand that. It's just like the thing that I invented. It hasn't changed, but it's poised for change. And it's really storage, so getting smart is a big change. Storage is the second big change. And so there are plenty of markets there. We're a little bit young to be credible, but if we can get these roadmaps going, as we're trying to do, we could maybe get some interest from Elon Musk, although he tends to stick to himself pretty much. But you might even, if you had a 5 times better and cheaper battery, I kind of think Apple might be interested. And, so there are opportunities there. That's a little bit what Jeff is working on.
Time for one more.
Yeah, you mentioned about frequency modulation.
Yeah.
In terms of applications. Now, what's the kind of response time and the amount of storage? I was thinking in terms of, can it be utilized for, let's say, in a situation where you have grid instability?
Oh, sure. So reliability is one of the big things. So the regulators tell the utilities, don't you ever let the electricity go off. That's your top priority. And they're pretty good they're starting to get smart, that is, the grid's starting to get smart. And they know how to, they have a lot of experience with that. They have to build for the peak, right? Because if the hottest afternoon in August, got to have enough electricity for it. So it's kind of expensive. If you had storage, you could do it a lot cheaper. But I think your question is, how reliable would it be? So if you had a big bank of batteries, and every second or half second you're either charging or discharging, you can take a lot of the uncertainty or a lot of the fluctuation out of the grid. There are ways of doing that. There are some batteries on the grid now. It's hardly any at all. But they have the fast response time that's required. So this is really a growth area. This is one of the things that Sandia identified. It's even profitable in PJM right now to do that. So that, for sure, is an opportunity. Now, that kind of battery, you want it to be fast charge, discharge. You don't need a lot of energy. So it's not the battery you would put under the hood of a car, and it's not the battery you would put next to a wind farm to back it up. It's a battery just strictly for that. It's very specific. We can design for that, and we're not at that stage yet, but certainly we could design for that kind of a use.
Okay. Thanks, George, for an excellent presentation.
Thank you.